Hello, my name is Keren Dayan from the Universidad Politécnica de Tapachula, and it is my pleasure to present my work entitled Galvanized Reinforcing Steel Performance Under Marine Environment in Concrete Prepared with Partial Replacement of Cement by Recycled Glass Powder. As introduction, we have embedded steel has a cycle protection when it is in concrete due to a barrier effect. However, the protection can be improved by means of a pore site densification that avoid contaminants such as chloride ion, research the steel and carbon dioxide damage the concrete. An option to this is the use of supplementary pozzolanic materials, such as recycled glass powder, RGP, in the concrete mixture. The objective of this project is evaluate the performance of concrete mixes incorporating RGP as a partial replacement of cement, comparing the corrosion behavior in commercial and galvanizing reinforcing steel rebars. The methodology of the work is divided in 4 steps. In the first step, we obtaining RGP. We start with collation, crushing, and grading, and ground to an average particle size of 30 micrometers. In the second step, the sample preparation, concrete samples were prepared using only OPC 30R for the blank samples and OPC 30R plus a partial replacement of 10% of RGP for the experimental samples. And 2 types of samples were divided in 4 water cement radius of 0.4, 0.5, 0.6, and 0.7. For the corrosion test, concrete samples were prepared embedded with 2 types of reinforcing steel rebars. Rebars with zinc coating and rebars without coating. And the experimental cell was left as shown in figure 1 in this case. In the third step, the samples were exposed for 24 months in Telchac, Yucatan. As you can see in the figure 2, we have Mexico, Yucatan, and the site of exposition, Telchac. These are the coordinates of the exposure site. The site was 2 meters above sea level and 50 meters from the coastline. An annual average temperature to 25 to 27 Celsius degrees. The rainfall average from 760 to 1 miles 470 millimeters, and the relative humidity from 75 to 77%, and this place it is a highly corrosive marine environment identified by ISO 9223 in 2012 as a classification CX in this case. And for 4 steps in measurements, the following tests were carried out to mechanical strength, depth of carbonation, chloride penetration, corrosion potential, and corrosion current intensity. For the results of the obtaining, we begin with mechanical strength. Figure 3 shows the evaluation of the mechanical strength in the 4 water cement radius 0.4, 0.5, 0.6, and 0.7 at 28 days, comparing the composition with and without partial RGP substitution. The results are not so different between the same radio, and this can be related to the pozzolanic activity of the glasses, as previous studies have shown that is not fully active at 28. 28. For carbonation and chlorides in the figure 4, we compare the 24-month exposure period against the depth of carbonation in part A, depth of carbonation in millimeters, and chloride penetration in part B. In this case, we have the chloride threshold, and the corresponding measurements were taken every 3 months, showing that the higher the water cement ratio, the greater the carbonation and chloride ingress. However, with RGP in proportion of 0.4 and 0.5, chloride ion and carbon dioxide penetration decreased significantly due to the deacidification of the matrix. This be seen quantitatively in figure 5, which shows that at 28 days, mixtures with RGP offer slightly greater potential against carbon dioxide. Although the difference in protection is more comparable between water to cement radios, with the uncolored areas begin those that have already been penetrated by contaminants. In other words, we obtaining a high densification of pores at a lower water to cement ratio. In the other hand, figure 6 shows 4 graphs. Parts A and B indicate the performance of the corrosion current density, with range limits first mentioned by Gomez and Andrade in 1988, comparing reinforcing steel rebars with and without counting. In part C and B and D, the graph shows the performance of the corrosion potentials, with limits mentioned by the ASTM C87691 standard, comparing reinforcing steel rebars, zinc coated and without counting, and taking into account the comparisons of the physical protection offered by 4 water cement radios. Finally, in the figure 7, same image of cement plus RGP to 0.4 water cement radio, 0.5, 0.6, and 0.7 show the composition of the 4 water cement radios with the presence of RGP and are visible in the indicate areas where we see traces of unread RGP particle in the mixers. This can be identified due to their angular morphology, especially with water to cement radios 0.6 and 0.7. This ties in with what I explained about the low variability of the mechanical strength in the samples. Our conclusions are RGP offers improved mechanical strength properties to reinforcing concrete. At radius 0.4 and 0.5, chloride ion ingress is reduced in the figure part B, reducing corrosion in the reinforcing rebars. At 28 days, the RGP is still undissolved, so it is not reflected in the mechanical strength. The use of zinc coated in reinforcing steel offers passive protection. And finally, here are some references consulted for the creation of this poster.